So I wanted to do a few more examples of the chain rule, and what I did was I pulled some stuff out of the book, and let's see what we got here. So it says find the equation of the tangent line to the curve at the given point. So the first one we don't really need to work on it. The second one, number 52, though, it says y equals square root of 1 plus x cubed at 2, 3. So what you would do is you would immediately write this as 1 plus x cubed to the 1/2 power so that you can use the power rule. You take the derivative using the chain rule, so that's 1/2 times 1 plus x cubed. 1/2 minus 1 is negative 1/2. Basically what I'm using here is x to the n. Take the derivative of that, it's n, x to the n minus 1. All right, now you take the derivative of the inside, 3x squared. And so derivative of the outside, derivative of the inside. It's the outside, this is the outside, the whole thing is the outside. And then, but you're plugging in the interior, and then you take the derivative of the inside. So out and then in. Now let's simplify this. We're going to pull this 3x squared over to the 1/2 right there, and we're going to get, looks like it's going to be 3/2 x squared 1 plus x cubed to the negative 1/2 power. And now I'm going to pull that down, and so it's 3x squared over 2, and it looks like it's going to be square root of 1 plus x cubed. All right, so probably should put more steps in there, but I think you get it. So let's see, so it says at 2, 3, so we're going to find, it says at 2, 3, so we'll find y prime at 2. That's going to be the slope of the tangent line, or whatever this thing looks like. And when we plug in 2, we get, looks like it's going to be 12 over 2 square root of 9. So that's 12 over 2 times 3 is 6. So this is 2. So the slope of the tangent line is 2 to this curve right here. All right, and now so we're going to use y minus y1 equals m times x minus x1. So we get y minus 3 equals m, which is now 2 times x minus 2. I'm just using those points there. And so we get y minus 3 equals 2x minus 4, and we get y equals 2x minus 1. Okay, so whenever you plot this on Wolfram Alpha or your favorite graphing device or whatever, you're going to get the following graph. Let me blow this up a bit. And let's see what's going on here. We have here the line. This line is 2x minus 1. We have this line. And then we have the graph, which is, and we have like blue here, purple, that's the graph. And so at 2, 3, we have the slope of the tangent line there. We have a tangent line, and so everything's working out like it should. All right, so let's try another one that involves a couple of different things. So we have y equals x times e to the negative x squared, and then at 0, 0. So we have an f, we have two functions, f and g. So y prime will be f prime g plus f g prime. So we're going to get f prime, derivative of x is 1 times g e to the negative x squared, plus f, which is x, and then g prime, so that g is e to the negative x squared. And in a previous video, I said that e to the u, when you take the derivative of it, you get u prime e to the u out of this. So what we'll get here is we're going to get u prime, which is negative 2x, and then e to the negative x squared, like that. So it'll be x times, we're going to pull this up, negative 2x e to the x squared, like that. All right, and so we're going to get, looks like an e to the negative, I'm sorry, it's a negative there, negative x squared. We can pull that out, and what's left is x. Well, I'll tell you what, that's the first one, that's that one. And then the second one is looking like it's negative 2x squared e to the negative x squared. And so we can pull out an e to the negative x squared, and we get 1 minus 2x squared out of this. and we're going to find the slope and the equation of the tangent line at 0, 0. So let's see here. So this is y prime. So y prime at 0 will be e to the 0 times 1 minus 2 times 0, which is 0. So this is all just e to the 0, which is 1. So this is 1. So we go y minus y1 equals m times x minus x1. And we get y minus 0, because the point is 0, 0, equals 1 times x minus 0. So basically we just get y equals x. All right, so that's the tangent line. And so what I'll do is I'll go to Wolfram Alpha and graph these two. All right, so let's see what this looks like. Here we go. Let's pull this up a little bit. So what we have in the blue graph is that x e to the negative x squared. So we'll just do that in light blue. X e to the negative x squared is the graph there, and then the y equals x, that was there in purple. And that's putting them both together. Now, if you notice on this graph, there are values at which the tangent line is horizontal here. All right, and I just want to go over that real briefly. We're going to get to that later, but it's worth going over now. Where it's horizontal is where the derivative, so this was the derivative, it's where the derivative is 0. So what we're going to do is we're going to take this and set it equal to 0, 1 minus 2x squared. And when you set this to 0, you need to understand that e to the e is never 0. So e to some power is never 0. So basically e to the negative x squared looks like this. And no, it doesn't. It looks more like this. So it's always above 0. So you're only going to set this to 0. I need you to convince yourself that this is never 0. So when you set this to 0, you get 1 minus 2x squared equals 0. 1 equals 2x squared. X squared equals 1/2. And then x is plus or minus 1 over root 2. And 1 over root 2 is about 0.71. And so when we look at this at 0.71, we should get a horizontal tangent line. And yeah, I mean, this is 0.2, 0.4, 0.6, 0.8. Yeah, about 0.71 is there. Negative 0.2, negative 0.4, negative 0.6. Yeah, sure enough, somewhere in there. And so it checks out like it should. All right, so here's the next one I want to do. Basically, we have the equation for a star's brightness. It alternately increases and decreases, the brightness does. So you have the brightness, basically you have B is the brightness and T is the number of days. So brightness is going up the y-axis and T, number of days, is going along the x-axis. All right, and so the maximum brightness here, from one maximum brightness to the next maximum brightness, is about 5 days. So it's 5.4 days. I think that's what it says right here. The interval between times of maximum brightness is 5.4 days. So it goes up and down, up and down, up and down. So sine is a perfect, sine or cosine are perfect functions to deal with things that are periodic, phenomena that are periodic. So we have that. The average brightness of the star is 4, and its brightness changes by 0.35. And so what they've done is they've created this. This you can do in trig. So what's the calculus? It says find the rate of change of the brightness after t days. So the rate of change, always think of this as your derivative. So what we'll do is let's go ahead and just write b of t down. So b of t is 4 plus 0.35 sine of 2 pi t over 5.4. Now when you take the derivative of this, let's just look at this for a second. You can write this sine as sine of 2 pi over 5.4 and then put the t to the side so that you have your coefficient pulled off to the side so you can take the derivative cleanly. It's kind of like writing sine of 3t, all right? The 3 is all by itself there. It's not mixed in with the, you know, like in a fraction. So when you take the derivative of this right here, okay, we're going to use the rule which says sine of u when you take the derivative, this is u prime times the cosine of u. So when we do that, we're going to take the derivative of the interior, which is this piece here. That's just a little polynomial. All right. I mean, yeah, it's polynomial. It's like having 3t, so the derivative would be 3. So this will be 2 pi over 5.4, and then times the cosine. So I've done this piece, times the cosine of the same stuff that's inside. So 2 pi over 5.4 t, like that. So that's the derivative of that piece. So let's go ahead and take the derivative of b itself. So b prime of t is the derivative of 4 is 0 plus, and then 0.35 times the derivative of what we had. So we'll do 0.35 times, and then we're going to take all of this and pull it down. So that will be 2 pi over 5.4 times the cosine of 2 pi over 5.4 t, like that. And so when you do the math here, you get 2 pi over 15.3, 15.4, it looks like, 15.4 times the cosine of 2 pi over 5.4 t, like that. So that's b prime of t. So what are they asking us to find here? It says find the rate of, after t days, find the correct distributable rate of increase after 1 day. 1 day. So we're just going to plug in 1 here. So we go 2 pi over 15.4. And I mean, since you're doing all this on a calculator, you can get the decimal approximation for that right away. And then so t is equal to 1. So we're going to get cosine of 2 pi over 5.4. All right. And so when you do this on the calculator, you get about 0.16. So that's, now you have to remember, you have to use radians in your calculator whenever you do this problem, okay? You have to use radians there. So 0.16, let's see what that looks like on the graph. Let's see if this makes any sense. So let's see here. 0.16 at 1, let's see. Yeah, it's going to be like a little positive slope there. So basically what that means then is that, so what does 0.16 mean? It means that the brightness, so this is 0.16 is like 16 over 100, right? So the brightness, the change in the brightness over the change in time is 16 over 100. So for every 100 days, it's 16 times brighter. The brightness increases by 16. But that doesn't make any sense because there's only 5 days here, right? So let's say this for every 1 day is 0.16. So at 1 day, because this was at 1 day, the brightness is increasing by 0.16. And there you have it.